Pilots take to the air, fly and survive due to skills acquired through basic training and subsequent practice, both leading to that all-important word, experience. Sadly, there are those who, on obtaining a license, imagine that the learning period is over. It isn't. The need for learning is constantly with us. Unplanned learning from close shaves is not acceptable. Avoiding them is the key to survival. Weather plays a vital part in a pilot's flying life and is thus an important part of the ongoing learning process. Many student pilots seem put off by the theory aspect of meteorology. Maybe a tutor at one time went too deep into the subject, or maybe study was based on a textbook that did the same thing. The need-to-know elements are not complex, certainly not for a simple understanding of clouds. Unfortunately, there is a gap in some textbooks. They are devoid of sufficient cloud pictures, no doubt due to the high cost involved. The aim of this video is to fill such a vital gap, to be a supplement to those textbooks. It is geared to enhance your ability to read and interpret clouds, so making a major contribution to your safety. Although a basic knowledge of theory on the part of viewers is presumed in this film, a brief recap on fundamentals would not be amiss. The amount of water vapor, relative humidity, present in a parcel or mass of air has a direct bearing on the formation of clouds. Warm air can contain more water vapor than cold air. So for a given amount of vapor present, the relative humidity decreases as air is warmed. The reverse takes place as air is cooled. Continued cooling can see the point reached where the air can contain no more water vapor. Relative humidity is now 100%. The temperature at which this occurs is known as the dew point. Further cooling beyond this point can result in the excess vapor condensing into visible water particles, cloud. Normally, temperature will decrease with any gain in height, and this can vary from level to level. The decrease in the atmosphere at any given time is the environmental lapse rate. Due to constant change, readings are taken at intervals each day by ascents made from observation stations. However, dry air forced to rise up through the atmosphere will always cool at a fixed rate of 3 degrees centigrade per 1,000 feet, or 330 meters. It's called the dry adiabatic lapse rate. When condensation takes place, the fixed rate reduces to 1.5 degrees per 1,000 feet, or 330 meters, due to latent heat given off during condensation, called the saturated adiabatic lapse rate. This reduction in the saturated rate begins to narrow above 6,000 feet. When the environmental lapse rate is under 3 degrees, rising air would soon be cooler, denser and heavier than its surround, and would therefore sink back to the ground. The atmosphere is then said to be stable. When the environmental lapse rate is greater than 3 degrees, rising air would be warmer, less dense and lighter than its surround, and therefore would continue to rise. The atmosphere is now unstable and turbulence can be experienced. Should condensation take place, the lapse rate reduces to 1.5 degrees in the cloud, making the now wet air even warmer than its surround, thus accelerating the ascent. Air can be forced to ascend and reach condensation level in various ways. It will rise on meeting up with high ground, such as a range of mountains or hills. Turbulence can lift moist air and mix it with colder air, thus cooling it to the condensation point. The upper air can speed up, and on leaving a region it can cause a temporary gap until the air behind it catches up. The result is air ascending from the surface to fill this gap, cooling adiabatically as it does so. A warm air mass, on catching up with cooler air, being less dense, has to climb over the cooler air ahead of it. Uneven surface heating can cause a massive parcel of air to become warmer and less dense than its environment. Given an unstable atmosphere, it will continue to rise and condensation may eventually occur. So much for the basic recap. Now on to the clouds themselves. Meteorologists break clouds down into a number of different types and variants. The basic classifications are high, medium and low, defined by the height of the base above the ground. Base heights can vary substantially with the seasons and the location in the world, with each or both affecting the height up to which the tropopause can reach. From the approximation shown, it can be seen that with the marked differences there may be times when assessment can be difficult. The ability to overcome this problem will come with practice. There is a further subdivision into two categories which define the format of a class of cloud. Stratiform, which is a layer or sheet format, and cumuliform, which is a heaped format. Within the stratiform and cumuliform categories there are many types. Clouds have Latin-orientated names, quite lengthy at times. In such cases we will stick to abbreviations where possible. So what are these types? We'll start at the high level and work our way down. High clouds are of a white fibrous format known as cirrus and are virtually transparent. This is because, unlike other clouds composed of water particles, high cloud is composed of ice crystals. Ordinary cirrus is composed mainly of wisps and strands with no other really defined shape. On occasions the strands can turn up at one end, and hence the name mare's tails. Cirrostratus can appear as a thin veil which sometimes covers the whole sky. At other times it can be seen as separate sheets. The sun or moon will appear through it, and on occasions a halo is produced. Cirrocumulus, or cirroq as it is known for short, is composed of sheets or patches of small globular-shaped clouds. It is also one type of cloud which can form what is commonly known as a mackerel sky. Again, the sun or moon will shine through it. Descending to medium level, there are 7 major types of medium cloud, 5 of which are stratiform and the other 2 cumuliform. Taking stratiform first. Altostratus is composed of grey sheets or one continuous sheet of cloud which is thicker than cirrostratus and not so fibrous. When thin, the sun can be seen through it, but it will appear opaque. Nimbostratus is an extension of altostratus, eventually reaching down to low cloud level. It is associated with frontal conditions. It has an amorphous look about it, with no defined shape, the base being obliterated by rain. Fractonimbus is a variant of a type rather than the type in itself. It is fragmented pieces of cloud formed when air under nimbostratus is saturated and lifted up to condensation level by turbulence. It can be called scud cloud. Altocumulus is a grey or white lumpy form of cloud which can exist in separate sheets or can merge into one single sheet of globules. It will resemble cirrocue but appears to be larger, being nearer to an observer on the ground. Again, like its higher counterpart, it can adopt a rippled pattern at times. Altocumulus lenticularis is a cloud much sought after by glider pilots. In appearance, it is a curved grey or white, almond or cigar shape, formed at the crest of a wave in an oscillating airflow set up to the lee of high ground. Unlike other clouds, lenticulars remain stationary in the sky. They do not drift with the wind. There are two types of medium cumuliform cloud. They both portend instability at upper levels, which can lead to thundery conditions. Altocumulus castellanus are small white cumuliform or heaped clouds which appear in rows at medium level. They have a flat base and hard turreted tops. Altocumulus floccus are ragged white clouds with no defined base, but they do have cumuliform tops. Floccus is easily identified by the swept-back trails or fall streaks known as virgar emanating from their base. First, we'll deal with the stratiform types, of which there are two and one variant. This type is normally associated with a stable atmosphere with no severe turbulence. Stratus is greyish in colour and devoid of any shape. It can appear in one single sheet or separate sheets. Fractostratus is a variant of stratus. It is composed of wisps found when stratus is forming or breaking up. Similar to altocumulus, but again larger due to being nearer the ground, grey and lumpy, it can appear as individual clouds or be merged into one sheet. When merged, it is easily distinguished from stratus, having a defined undulating shape both in base and top. It can also appear with the parallel rolls similar to cirro and altocu, and lenticulars are quite possible in the lee of high ground. The cumuliform category of low cloud, cumulus, is primarily a result of convection with its usual turbulence. Small cumulus is actually known as cumulus humilis and is designated such when the top is well formed and the base is flat. The description small applies when the base width is greater than the height. If no further growth takes place, it is often referred to as fair weather Q, as it does not pose a risk of bad weather to come. Fracto Q is the first cumulus variant we come across. It can vary from a wisp of newly forming cumulus to a ragged lump of same. It will not have the flat base and crisp top of actual Q cloud. Cumulus actually becomes defined as large when the height exceeds the width. In meteorological terminology, there are two types. Mediocris, when the height is said to be moderate. The other type is called congestus, when the cloud becomes towering and displays those well-known cauliflower tops. It is quite possible to see the tops forming when the growth within the cloud is vigorous. Should the crisp tops begin to appear ragged, it can be a sign that the cloud is decaying. On the other hand, fresh growth might appear at the sides, showing new convection cells forming. Should a Q cloud reach a stable layer at medium or low level during its ascent, it can no longer climb. However, if the convection continues lower down, the ascending cloud will spread out to form a layer on reaching the invisible ceiling or equilibrium. It is called alto-Q or strata-Q genitus because it has been generated by cumulus and not by the usual process. Here we come to view the most powerful cloud nature can produce. It quite rightly brings a chill to the heart of any sane pilot in view of the extreme turbulence and icing it can generate. Starting as a humble small Q cloud, the Q-nim begins to develop from the congestus stage when the tops remain solid, but the cauliflower effect is replaced by a smoother, baldish sort of appearance known as calvus. The next stage will be the spreading out of wisps and strands in an upward direction. This is known as capillatus, and it is composed of ice particles when the condensed water droplets freeze as glaciation takes place. As the Q-nim reaches the tropopause, it will cease to climb and the top spreads out. In faster upper winds, it forms an anvil shape. The underside of the anvil will appear as altostratus or nimbostratus, and it is known as incus, but this time the composition will be of ice particles instead of water droplets. Any precipitation from the anvil will be of snow, but it will evaporate before reaching the ground. This alto or nimbostratus can stretch for many miles downwind at times, to the extent that the source Q-nim can be out of sight. Mammatus, or mamma cloud as it is called, can form under the incus section of a Q-nim. Due to latent heat, the interior of the cloud can be relatively warm compared with the outside at such a height. So, a cold skin can form on the exterior of the incus, which becomes denser and descends to form globules giving an udder-like appearance. Diverting for a moment, mamma can also appear under alto cloud, for the same reason it does under Q-nim incus. Although mamma may appear very ominous, it is not so in itself. But back again to the Q-nim. Fall streaks of cirrus-type cloud can form at the extreme top of an anvil, as ice crystals which drop away and then evaporate as they warm adiabatically. The name given to this type of cloud is the biggest mouthful to be found in the study of clouds. It is cumulonimbus cirrus spisatus genitus, commonly known as cirrus spisatus. Cirrus spisatus hangs around long after a Q-nim has decayed, and particularly attractive sights can be seen at the end of a stormy day. Having covered clouds at all levels above the surface, we now look at cloud or condensation at ground level, in the form of mist and fog. Mist is composed of microscopic water particles which affect visibility but do not reduce it below 1 kilometre. By international standards, fog exists when visibility falls below 1 kilometre, but in the United Kingdom the term is not used until visibility falls below 200 yards, or 180 metres. The most common type is radiation fog. Normally it forms on autumn and winter evenings or early morning in spring and even summer. First appearances are most likely in valleys where rivers or streams speed up the saturation of the air. Radiation fog will continue to spread and thicken while conditions remain relevant. Clearance normally comes about in one or two ways or a mixture of both. They are a strengthening wind or the sun's warmth lifting it away from the surface to low stratus level. It is closely associated with anticyclones, and in the colder seasons it may persist all day on the surface or as a layer of stratus often referred to as anticyclonic gloom. Fog forming on the slopes of hills is termed hill fog, but viewed from the ground it will appear to an observer as low stratus. However, if your base is on high ground, then the effect is fog, whatever it looks like from the plains below. In looking into how clouds can warn us of adverse weather, we'll start with fronts. There can be two basic systems plus a variant. They are the Anna system, with a stable and an unstable cold front, and the Kata system. The Anna front occurs when the general atmosphere is ascending and therefore cooling. This allows rising frontal air to reach high levels as it continues to be warmer than the air through which it climbs. If not due to a declining sun, the first sign can be cumulus cloud lessening or decaying with increasing cirrus above. The cirrus thickens into cirrus stratus towards the west. The base lowers as the front approaches, eventually reaching down to become thin altostratus, where the sun may be just visible. As even thicker altostratus follows on from the west, rain or snow will begin to fall. Initially, it will evaporate before reaching the surface. As the front gets nearer, the cloud base drops still lower, and continuous rain or snow sets in, which obscures the base of the nimbostratus cloud, producing the precipitation. The nimbostratus can be accompanied by fractonimbus, scud cloud. As the warm front passes, the rain will ease off, become sporadic or even stop. The clouds once more begin to show some shape in the form of strata Q and stratus. We are now in the warm sector, and there will have been a veer in the wind direction, well defined if the front is vigorous. As the cold front follows on, the strata Q will thicken and deepen. Once more nimbostratus forms as the warm air is now undercut and lifted by the cold air. Continuous rain or snow will recommence, but the duration will be much shorter. Eventually the rain eases off, and to the west appears a brighter sky. Once again there will have been a further veer in wind direction. In the case of an Anna cold front, the rear can display a sharp, well-defined line in the sky from horizon to horizon. If the cold front air is unstable, the nimbostratus is replaced by Q and Q-nim, producing very heavy rain and even thunder. The cold sector, following a cold front, is normally composed of a polar maritime airstream which can produce cumulus and Q-nim with subsequent heavy shower activity. Here is a cross-section of a classical frontal system which depicts an unstable cold front. The colours depict cool, warm and cold air from right to left. With a catafrontal system, the environmental air is descending and warming, so clouds can no longer reach up to a high cloud level. The first sign of a cata-warm front will be increasing stratoQ in the westerly quarter of the sky. This cloud gradually increases and thickens until eventually it merges into one continuous sheet, although the shape will still be visible. Rain or snow will fall, and if heavy enough, the cloud shape may disappear into an amorphous type nimbostratus format. However, rain in a cata system is not so intense as in the Anna system. The clouds do not have the vertical depth to hold the same amount of water particles. As the warm front passes through, again the rain stops or becomes patchy and the wind veers. We are now in the warm sector of the system, where the sun may or may not break through at times. When the cold front approaches, there is a virtual repeat of the warm front. Once again, there can be a period of continuous rain. The passing of a catacold front will not be so pronounced as the Anna type, but there can be a Q and Q-nim build-up following on. Here is a cross-section of a catafrontal system. Again, the colours depict cool, warm and cold air from right to left. It is essential to back up knowledge gained in cloud recognition with an awareness of forecast weather systems. Fronts are frequently associated with depressions, so if you feel the sky is indicating signs of a front, make a quick barometer check. If it's not showing signs of a fall in pressure, you may be misreading that sky. The BBC TV and one or two daily papers give pressure and frontal systems on their charts. The example shown depicts a prognosis on which such charts are built up. These points are made because sometimes all the signs can be there, but the front never materializes, such as that portrayed. Incidentally, climb up through a front, hopefully suitably qualified to do so, and you can find that it is not necessarily solid, but can be composed of layers of cloud. Finally, you must appreciate that with meteorology being an inexact science, fronts fall in line with this thinking. Rarely are two fronts ever exactly the same. They can be weak or vigorous, ana or kata, or a mixture of both, and they need not be associated with a depression. So much for fronts. However, if one is approaching, fly towards it when enjoying that hour or so in the air. You would at least be sure that the route home is clear. Go the other way because the sky looks more inviting, and the return trip could be quite stimulating. We'll now take a look at the next type of adverse weather situation of which the sky can give a warning. Thunderstorms are no friend to a pilot, but fortunately the clouds can provide a pretty good indication of their development. The cloud uppermost in one's mind when thunder is mentioned is the Q-nim. Apart from those associated with the passing of a cold front or a very unstable polar maritime airstream, the thunderstorm is primarily associated with hot, humid air in an unstable atmosphere, perhaps with a decline of an anticyclone at the end of a heat wave. The problem is that with anticyclones there is often thick haze, and this can obscure the Q-nim build-up until slowly it dawns on one that the sky has darkened and begun to look ominous. Invariably, it will also be calm or with little wind, plus a sticky feeling in the air until the storm breaks. We now look at a thunderstorm sequence which within 1 hour was able to transform a perfect summer's day into a deluge. Initially, the sky showed only fair weather Q. This gave the impression that all was indeed set fair, particularly as it had not grown by this time of day into large Q or Q-nim. Cirrus began to appear to the south, which was not identifiable at the time as being Cirrus spisatus from the top of a Q-nim. It took only a little more time before Q congestus appeared through the haze to arouse suspicions. Soon the cumulus congestus was joined by Q-nim, and it was obvious that a storm was about to break in the area within a very short space of time. This prognosis was verified by the intensely black sky that developed to the south. As the sky blackened even further, distant lightning was seen and thunder could be heard. Finally the storm broke with thunder and lightning overhead, accompanied by very heavy rain. As the storm passed over, it left a very chaotic sky. But not all thunderstorms start at low level through uneven surface heating. Altocumulus castellanus is a sign of instability at medium level, brought about when a pool of cold air breaks away from an upper air trough extending down into temperate latitudes from the Arctic regions. It is a good indication of thundery tendencies in the offing, as is Altocumulus floccus, at least within a radius of approximately 100 miles. Here we have Castellanus, and you can just see Q-nim giving thunderstorms 75 miles away, but not affecting the point of observation. Castellanus and Flockus can appear and disappear without anything happening. This next thunderstorm sequence at medium level took from 11 AM to 3:30 PM to manifest itself. The first sign was sporadic altocumulus castellanus clouds in the sky. These gradually developed during the course of an hour. After about 3 hours, the sky was totally covered with the castellanus format of the cloud, no longer identifiable, having only a thick altostratus appearance. The sky then took on a nimbostratus format with heavy rain and thunder occurring 9 miles to the west. The storm continued on a northerly track, with the thunder and rain continuing. You need Q-nim for thunder and lightning to occur. In the case of this format of thunderstorm, it is obscured by the castellanus cover, which now has that nimbostratus appearance. The extreme turbulence associated with a Q-nim should justifiably bring a chill to the heart of any sane pilot. The power inside it is awesome and at times resembles another source of power to be feared. Important to note is the effect of a Q-nim on local winds. Pilots have been known to check the windsock, select their takeoff direction, and on takeoff have experienced difficulty in gaining a safe flying speed. Whilst taxiing out, the wind had reversed due to a Q-nim, albeit some 10 miles away. Cold upper air sweeping down and out from a Q-nim can meet inflowing surface air, creating the calm before the storm. The cold air then takes over, undercutting and lifting the warm air ahead into a line of roll cloud. A sudden strong squall can develop and damage untethered light aircraft. Pilots have often wondered why their rate of descent has increased sharply whilst the airspeed and engine revs are normal. There can be descending air surrounding a Q-nim within 15 miles radius. The clear sky around the cloud indicates the descent by the lack of condensation. A similar effect can take place with no Q-nim present. Recall the lenticular cloud. An increased rate of descent can occur when you are in the downwind side of the wave which caused this cloud. These waves can continue to be effective many miles downwind of their source point. They can also occur when no lenticulars are in sight. Either way, move to right or left of your track to escape this effect. Faced with a line of Q-nims en route, a pilot may seek a gap of blue sky and head for it at a last-minute chance to avoid a diversion. This gap is known as the sucker's hole. This one closed up in less than 3 minutes and had been 5 times the size only 4 minutes before. This airship hovered for over 45 minutes awaiting a safe passage. You can do that with an airship. Low stratus and hills do not make a good combination. Coastal areas are particularly prone to this hazard when a moist onshore wind is blowing. This helicopter changed course to ensure a continued safe passage. 5 minutes before, the 900-foot hill was clear. The pilot was wise to do so, because here is the top of that hill a few minutes later. Visibility, or perhaps the lack of it, is a critical aspect in flight safety. Apart from flight in cloud, the main causes of poor visibility in order of ascendancy are haze, mist and fog. Unlike cloud, haze is composed of particles of matter such as dust, not condensed water particles. Although infrequently, haze can reduce visibility down to 1 kilometer, and therefore it should not be ignored. particularly when flying up sun. Should haze limit surface visibility down to 1 kilometre, bear in mind the ground will be out of sight at a height of around 3,200 feet. Mist can be similar to haze in its effect on visibility on the ground and from the air. Being composed of water particles, it is only one step down from fog, which means it may be the forerunner of fog. It is frequently associated with low stratus conditions and can cause difficulty in accurately assessing a cloud base. Finally, fog. Fog is not confined to those murky days when the temptation to fly is at a minimum. Sadly, radiation fog can form when cloudless skies see the temptation at a maximum. The times at which it is most likely to form were discussed earlier. It can form very quickly, so do think twice about that late afternoon flight in winter, as your field could be obscured within minutes after you have taken off. The sky is ever changing. Rarely will there be simply one type of cloud, but rather at times an infinite mixture. The art you must develop is that of identifying those which have a specific message to give you. Do remember to link any newfound knowledge to current weather charts and forecasts whenever possible, many of which are available by fax or phone. At the risk of repetition, it really would be worthwhile to consider becoming the owner of a simple barometer, or, if you can stretch to it, invest in a barograph. The latter will ensure you have a continuous picture of local trends at a glance. So ends our journey through the clouds and the weather associated with them. Taking to the air is a superb experience. It has captivated thousands of men and women since the invention not only of the aeroplane, but of the many other forms of achieving flight. However, like all adventurous activities, there is ever present the need for care. Unfortunately, weather continues to be the major contributor to accident statistics, particularly in the sphere of recreational flying. Read the sky and avoid being one of those statistics. If you have learned but one new fact from this film, it will have been well worthwhile.